Hello and welcome. Welcome to this presentation where we are looking at part 2 of topic 5. And we like to take a numerical example to demonstrate the significance of estimating a generalized function in one go. And so we like to look at example 1 first, where we have this time delay system, which was obtained from topic 1. When we did the decomposition, we obtained this reduced order time delay system, and we have this generalized functional. What we do here, we replace this output measurement yt and yt minus tau by this symbol expression. And so what we want to do is to take this numerical example, which was taken from chapter 4 for scenario 4. And in this particular example, when we do the decomposition, we required to estimate this delay stack variable directly. Okay, directly. And when you look into this, this A bar D21 is 0, 1. So basically, we require the estimation of a delay stack variable x bar 1, 2, t minus tau directly. There was no method available at the time. And so we like to take everyone through a journey of investigation and finding out what is going on in here. So we take this example where metric A bar 1, 1, A bar D 1, 1, D bar, I bar D 1, 1, B and C tilde as given here. Now, the metric C tilde 1 is a canonical form. So what this one telling us is the stack vector consists of two variables. We call them x bar 1, 1, the first variable, and the second stack variable. So for this example, the output measurement y bar of t is actually from the first stack variable. Now, as I mentioned before, there was an option 1, to realize this functional. We can realize the estimation of the stack variable first, instantaneously first, and then we delay it. So this is just to show that if we do that way, if we follow in that option, that meant that we need to estimate this unmeasurable variable first. And that means that is a classic stack estimation problem of a time delay system using existing results in the literature. You can call it a linear functional observer when we express it in this form. So the matrix F is that row matrix there. And of course, the FD is 0 because we want to estimate this instantaneously. So this functional itself is the classic functional functional that we used to have as normal in the literature. And that means that existing methods, for example, here we pick this reference. It's a well-known method for design linear functional observers for system with delay in the stack variables. And according to the method given in this reference, the functional observer, the one that given in here, or the one that is actually only consisting of that bit only, the proposed structure is of the following form. It's similar to the one that we proposed in the previous section. Whereas in our previous section, we have a bit more general expression. We have delay in here as well as multiple delays. So in here, according to this reference, that's the structure of the observer. And this observer, we call it the one with internal delay. And so the existing conditions, this is the, by the way, the necessary and sufficient condition for the existence of a solution to some metric equations. Yeah. And there are basically only two metric equations in there. In contrast to what we had in our development, we had three matrix equations. So this condition, if it is satisfied, that means that we will be able to obtain a solution for the unknown matrices for the observer. And so if we, on the other hand, if we, let's say we want to make it even simpler, we want it to be similar than this structure. So that means that we put n equal to 0. When we put n equal to 0, we actually removing this row block here and this row block here. So the condition is a little bit more conservative, but in this example, the condition is satisfied. However, the solution gives us an unstable observer, by the way. So this is the coding that I used to implement this method. So we got matrix A, B, C, and F, and FD. FD is 0, and then we construct that matrix there, and then we check the rank, and then we work out the solution for all the unknown parameters. And then what we do, we cut and paste it in there. The significant finding of this bit is that we got the solution for metric X, which basically has an unstable pole, and the rest of the observer parameters, they are all 0, as well as the solution bits, the generalized solution that we discussed previously, where we say that there is also an extra degree of freedom in this solution if this one is non-zero. It happened to be that for this example, that term there, which is OD multiplied by the small Penrose inverse of OD, is actually an identity. Is actually an identity matrix, and that what that means is we don't have any freedom left in here, so we only have this particular part of the solution. And if that, in that case, that's why we can't do anything about it. And the solution itself gives us an unstable fixed pole in there. An unstable fixed pole. And so what happened in here is, well, we say that if we apply this method, and if we just use the one with our internal bits in here, internal delay in there, we are in trouble. We can't estimate this unmeasurable stack variable because we have an unstable system, unstable observer. On the other hand, when we don't remove that row block in there and we test this condition, in other words, we're going to use this extra term, which is an observer with internal delay, then the condition is satisfied. Still, because of course, if this condition is satisfied for ND equal to 0, it must satisfy for ND not equal to 0. Now, what I like to do is to show that when we modify those conditions, yeah, and then when we do the solution, we will have the matrix, the extra degree of freedom, the one that I refer to, that bit there is non-zero for ND matrix. Okay, let's have a look at that. So when we got this thing here, we got solution X, you got N here, and then that's ND. But this bit here is this first column is all zero. That means that we don't have any freedom or any freedom in this particular bit there. But we have for this bit in here. And this is zero as well. So we arrive at an error equation, an error equation, an error dynamic equation, which is a time delay system. If we want to ensure that there exists an observer that gives us an error goes to zero, then we need to find a scalar gamma in here. This scalar gamma happens to be, that whole column there. And then they got another row, so we can just replace that by single scalar. So we got this aerodynamic equation, and we want to find a gamma to ensure that this time delay system is stable for a given value of tau. Now, when we don't have an internal delay, of course, the system itself is an unstable system. There's nothing that we can do about it. When we introducing this internal delay term in the observer, that give us a little bit of freedom. Now, to ensure the stability of this error time delay system, there is an exact stability condition derived for a scalar time delay system. And that is given in this reference. So in this reference here, what the conditions are, we can have, even though this is an unstable term there, which is 1, we can select gamma in such a way that sum of 1 and gamma is negative number. So that is the necessary requirement. And on top of that, there is also another requirement that the value gamma here has to be bigger than -1 over tau, where tau is a given time delay. So these are the conditions, and that imply that if you want to ensure stability for this error time delay system, we can only guarantee it for a range of time delay. So that's the key thing here. That's still an improvement, but doesn't mean that we can always achieve for any arbitrarily or any given tau. Okay, imagine if this term here is getting bigger, that means that the time delay getting smaller. So the idea of estimating this unmeasurable stack variable first using existing method seem to be a problem here, because sometimes we might not always be able to do that. And this is example that demonstrated. Okay. And bear in mind that if the observer is without internal delay, definitely nothing can be done about it because of unstable fixed pole. Right, so what can we do? The other methods available in the literature, which we would like to mention in here, is also another method for design an observer to estimate instantaneously stack vector of this time delay system. Remember, we are estimating this instantaneous unmeasurable stack variable there. Okay. And that method is by Howe and Muller. Not Howe Muller, Howe and Zigzag and Patton. It's a very, in my view, an elegant method. Theory there is beautiful. The idea there is to introduce coordinate stack transformation, which is operators delay D in there. And the idea they're introducing this coordinate transformation, we can transform a time delay system where there are delays in the stack vector, like in here. That one will then be disappear, and then it move back into, it injected into the delay measurements and so on. And so we like to call it an output injection approach. And what is it about? It's basically introducing a delay operator where the time delay is expressed in terms of a metric with argument D in there, where D stands for the delay tau. And so it also applied to system with multiple delays in the output measurement vector. Now, what happened in this example is that when we look at this matrix and we got this delay operator, there is minus D and 2D, and this is 0, 0, 0, 1. We add them up, we obtain a matrix ID that put it in that simplistic way of explaining it. So that where it came from minus 1 and 2D xt minus tau, that where it become D operator in here. And then the other I bar 1, 1 is 0, 0, 0, 1. So we obtain this matrix. So we basically express the time delay system in this form. And so we can obtain matrix CD. Now it happened that there was no delay in the output measurement. So CD is just the C metric itself, and BD is the B metric itself. So this transformation enable us to transform the system into the new coordinate. So that's what it is. And when we examine this new coordinates, we got the pair I bar and C bar is in a specific structure, which is observable all the time. And then all the delay terms associated with the stack delay vector and all of that, they all injected into the output and the input of the system. So because output and input of the system are known, it doesn't matter how many delays you have in there. We can always design an observer to estimate the stack vector there. If we can transform, if there exists a transformation coordinate to transform the system into this coordinate. And according to Hao and Muller, the necessary requirement of sufficient requirement, even only condition is that this matrix here is column modular or unimodular for the case of a single output. It had to be for all value of S in the complex plan. So what we do is we construct this matrix where we have CD and CD times CID and so on, which is the one given in here until that become up to N. So this matrix here is a square matrix. And so what we do is we say, okay, for all value S in the complex plan, if this metric here where D is replaced by S, if this one has full rank, which is 2, or for all value of S in the complex plan, then if that condition exists, then there will exist a stack transformation to transform the system in this form. Now, unfortunately, for this example, when we apply the method in, we will find that we have a problem here because the determinant, in other words, the determinant is 0 if S equal to 0. Okay, so it's not unimodular. So as a result, we can't use the method. We can't use this method. And therefore, Hao-Muller method does not work. So if we need to realize this unmeasurable variable first, and then delay it by tau to realize this estimation in order to realize the asymptotic estimation of the unknown input, then we can't do it. So option 1 in chapter 4 is not possible. And so what is the way to go in here? Then we should estimate it that generalized functional directly. And so what happened in here is we need to choose the matrix F and FD according to do the following. So if we make this in this form, that means that Z bar of T is actually the one that we are looking for and the one we wanted to estimate. So if we do it directly, then that means we can estimate it directly. Okay, but at the time, there was no method available. So we were looking at alternatives and so on, but now we can do it. I also like to mention that in the literature, there are some methods that use text transformation developed in the following reference that allow us to estimate this delay stack vector or delay stack variable. Okay, but that involves tedious algebraic manipulations. And in the following is just a brief explanation of the potential that one can do by using these methods to realize the estimation of a delay stack variable. Okay, so bear in mind that methods that are used to estimate this stack variable does not work. Because if we do the one without internal delay, we got an unstable observer. If we do it with delay, we cannot guarantee. We can't guarantee it's stable for all value of tau, and so there's a restriction in there. And if we do the Helm-Muller method, the necessary requirement of modular does not exist, so we can't do it. There is a possibility of doing it by introducing this kind of transformation in here. With this transformation in here, we just say, well, let's pick something in here. Let's choose this new variable. We see the variable, we see y bar of t, but then the next variable is a combination of something there. So that's the key there. You know, what's something in there. And so there is a whole description of how we go about picking the transformations, which within my view is difficult to do. So when we do this transformation, we get this system in this form. We can substitute something in, and then the key is we are able to transform it into a new coordinate. In this new coordinate, the good thing about that is all the delay in the stack vector, they are now disappear. We don't have any delay in the stack vector and equation anymore. And not only that, this matrix and this C matrix here, they are observable. The pair is observable. And so all the delays are now injected into these terms here and the input as well. Now, if we can do it, of course, then we can design an observer to estimate this variable here. We can estimate this variable here. And if we can estimate it, then from this expression is the one that we introduce the coordinate transformation. So if we can estimate that variable, then of course we can estimate the delay of this stack variable. So that's the idea behind that. So we then say, oh, we can estimate this delay stack variable. And of course, then that can be used to realize the estimation of the unknown input, because the estimation of the unknown input requires us to estimate directly. Okay. However, we like to mention that this transformation approach involves very tedious algebraic manipulations. And we can show that by doing our new method, we can estimate that directly without any difficulty at all. We don't need to pick and choose what kind of transformation that we're going to have. And therefore, we can systematically derive the observed parameters by just simply checking some conditions. So with our new method, we then say, all right, we estimate this directly, which is choosing the F and FD according to the following. And that means that if we can estimate this directly, that means we estimate this delay stack variable. And in our development in the previous session, we introduced an observer structure, which is a bit general with all of these parameters, and we show that we can have the following conditions, which is basically the rank of this matrix and the rank of this augmented matrix had to be satisfied equal the same. And we can also pick an observer without an internal delay. So that's where we try first, because that always give us the simplified structure. And so we're going to plug in these matrices, and we obtain that and we check it. So that where I like to show the codings for that. And in here, this is the big ID and all of that stuff. And we do all the decomposition and we obtain the reducer, the time delay system. And then we pick the generalized functional where F is 0 and C tilde 1 is 1 and 0. And the one we want to estimate the delay FD 0, 1. And then we construct the condition, the matrices in there, and we check the rank. And then we obtain a solution, and we obtain the bit that give us the freedom, which is this thing here. Z, we call it Z in here. It's actually the one in here, the whole thing in there. And it's a good thing that that bit there is really give us non-zero term. And so we get a pair, which is the metric n, which is observable. And so what we did in here, we just pick a pole at -5, and we just simply work out the pole placement. We obtain Z, and then we get the rest of the matrix, and then we then pick those parameters of the metric X, where we pick N and D, of course, 0, T tilde, W tilde, and so on. And then we realize the rest of the observer parameters. And as you can see, it's done systematically. We follow the process, the procedure, and then we obtain the answer where in here the observer parameters or the observer structure is given by this form in here. Now, remember that this observer actually estimates the delay stack variable directly. Okay, it estimates this directly. And on top of that, we can arbitrarily assign the location of the pole. So the observer is very, very stable. It's independent of delay. And because we pick it at -5, we could have picked it any other values. It's still okay, no problem at all. And so we obtain that observer parameter there, and we can verify that. Let's say we can have n there. N is there, -5, and D is the one without internal delay. MD happen to be 0. We don't need that term in there, but there's sometimes we need it, and so on. And then we got G, GD, and so on. So that show that by using our generalized functional observer that we developed in topic 5, part 1, we can estimate the function in one go. We can estimate the function in one go. And we avoid the need to estimate this variable first and then delay it because it doesn't work. We don't need to do any sophisticated, tedious algebraic manipulations to arrive at a particular coordinate transformation and all of that. All we do is just substitute whatever parameters we have into the conditions, and we can systematically solve for the solution, ensuring that the error time delay system is stable. And so we got that. And that showed the significant, the advantage of what we developed in here, in this book, where we talking about generalized functionals. Of course, this generalized functional is a specific, which is the delay stack variable. It can be any combination. And so the theory itself allows us to estimate any linear combination of the instantaneous stack and the delay stack, any linear combination of it. So in the next topic, please join me for the next topic, where we continue to look for more examples to demonstrate the significance of generalized functional observers. Particularly, we will take 2 more examples for this class of time delay system, and we will demonstrate that we can design delay stack observer systematically by just banging the term FD in here, make it FD non-zero. That means that all the development in the previous stack transformation approach can all be unified by just design a generalized functional observer. Not only that, we're going to show that we can overcome some of the restrictions in previous work, where we can expand the dimension of the observer. We can expand it. And then with the introduction of the delay term in the functional, it can relax the observer existence condition. And it's lead us to an observer with a higher dimension than the redo of the system. So this is something very intriguing. That is something that we discover along the way, and it's fascinating. So please join me in the next few videos where we take 2 more examples to demonstrate the significance of generalized functional observer and for this class of time delay system. Of course, there will be many more development for generalized functional observer later on. So thank you very much, and bye-bye for now.